Hi guys, now we're in section 9.3, which is geometric sequences and series. A geometric sequence is one that has a common ratio. In other words, if you divide consecutive terms, you will get the same number every time. So in order to show that the sequence is geometric, what we want to do is find the common ratio. So let's go ahead and write out the first few terms, then we can divide them and see if we get the same thing every time, which we should. So t sub 1, the first term would be 2 to the first power over 3 to the 0 power, right? Because 1 minus 1, so that would be 2. Okay, then t sub 2 would be 2 squared over 3 to the first power, so 4/3. The third term would be 2 cubed over 3 squared, so 8/9. Now let's just write out one more. The fourth term would be t to the fourth power, 2 to the fourth power divided by 3 cubed, so 16 over 27. So if this sequence was geometric, I should be able to divide consecutive terms and get the same thing every time. So I'm going to take the second term and divide it by the first term. So 4/3 divided by 2. Let's go ahead and make that 2 over 1 so we can multiply by the reciprocal. 4/3 times 1/2, reduce, that is 2/3. Okay, let's also take the third term and divide it by the second term and make sure we get 2/3 again. We should, if it's geometric, we should also get 2/3. So the third term is 8/9, and the second term is 4/3. So I'll multiply by the reciprocal. Looks like I can do some reducing here. 3 and 9 have a common factor of 3. 8 and 4 have a common factor of 2, so I'm getting 2/3. Okay, so this will keep going. If you divide any two consecutive terms, you will get 2/3 every time. So that is our common ratio. It's 2/3. All right, this next one is asking us to find the nth term of the geometric sequence given the first term and the common ratio. So let's go ahead and list out some terms and see if we notice anything interesting. So the first term is 6. The second term would be the first term times the common ratio. So 6 times -1 over 3 pi. We can reduce that, we get -2 over pi. So notice the first term was positive, but the second term is negative. Let's take a look at the third term. The third term would be the second term times the common ratio. Okay, so I have a negative times a negative, that's a positive. I have 2 in the numerator, and I have 3 pi squared in the denominator. Okay, so we've gone from positive to negative back to positive. So this is an alternating sequence, and in fact, it will always be an alternating sequence when the common ratio is negative, because for your odd powers, it will be negative. For your even powers, it will be positive. Let's keep it going. So the fourth term would be the third term, 2 over 3 pi squared, times the common ratio. So this goes back to being negative, so I have -2 over 9 pi cubed. Okay, and only need to go one more to get the fifth term. So that would be the fourth term times the common ratio. So that would be +2 over 27 pi to the fourth. So there is an easier way to express the nth term of a geometric sequence. Notice that by the fifth term, we had 4 factors of the common ratio. So if we're talking about the nth term, it's always going to be the first term, in this case it was 6, times the common ratio to the n-1 power. So by the time we got to the fifth term, we'd already multiplied by 4 factors of -1 over 3 pi. So this is the general formula for the nth term. Let's try it and see if it matches what we got using kind of a recursive definition. So it should be 6 times negative 1 over 3 pi to the 5 minus 1 power, so 4. So 6 times a negative raised to the 4th power would be positive. 1 over 3 to the 4th power is 81 pi to the 4th. We can reduce 6 over 81. They both contain a factor of 3. So this becomes 2, this becomes 27. So it does look like we get the same thing, which we should have expected. It's not a surprise. It's just interesting to note how much easier I think it was to just find a single term once we have the formula for the nth term. And below we actually have it written out for us. In general, this is the formula for the nth term of a geometric sequence. So notice that you need the first term and you also need the common ratio r. So let's try this formula with the next example. Find the 10th term of this sequence. So I don't want to find 10 terms. I want to define a formula for the nth term, and then we can just plug in n equals 10 to find the 10th term. So we need the first term, which is negative 1. And we also need the common ratio. So from negative 1 to 2 and 2 to negative 4, we're multiplying by negative 2 each time. So that would be our common ratio. So let's go ahead and write out the explicit formula for the nth term. So it's the first term, negative 1, times the common ratio to the n minus 1 power. So let's now find the 10th term using that formula. So I'm finding a sub 10. So I'll replace n with 10. So it's negative 1 times negative 2 to the 9th power. So it's negative 1 times negative 2 to the 9th is 512. Actually, it would be negative 512 because that's an odd exponent. So the 10th term is 512. So for this one, we've been asked to find the nth term, but we've just been given some information about a few different terms. So the third term is 1/3, the sixth term is 1 over 81. With this information, what we can do is we can create a system of equations. So I'm going to use the general form of a geometric sequence and just plug in. So a sub 3 is 1/3, a sub 6 is 1 over 81. We can create a system of equations. So the sixth term is 1 over 81. We don't know the first term, we don't know the common ratio, but n minus 1 would be 5, right? Because this is the sixth term. So n minus 1 would be 6 minus 1, which would be 5. Now for the third term being 1/3, I'll just write it beneath. And then 3 minus 1 is 2. So I wrote the equations this way to show you something that I don't know if we've done this before. Maybe we did in our exponential chapter. But if you want to, you can divide equations to do elimination. So what I'm thinking is if I divide these two equations, I can eliminate a sub 1 because a sub 1 over a sub 1 is 1. So I think I'm going to do that. So I have 1 over 81 divided by 1/3 equals a sub 1 r to the 5th over a sub 1 r squared. So I'm canceling out the a sub 1's, or removing the factor of 1. 1 over 81 divided by 1/3. I'll multiply by the reciprocal. Here I can use the quotient property of exponents to just subtract. 5 minus 2 is 3. Okay, I can do some reducing here. 3 goes into 3 one time, 3 goes into 81 27 times. So I'm going to continue up here. So 1 over 27 equals r cubed. Cube root both sides. 1/3 equals r. So I now have the common ratio. I can take that and plug it back into either of my equations to solve for the first term. So I'll just plug it back into the second equation because it has smaller numbers. So 1/3 equals a sub 1 times the common ratio, which we found to be 1/3 squared. So 1/3 equals a sub 1 times 1/9. Multiply both sides by 9, and we get 3 equals a sub 1. So that means our first term is 3. And now we can put this information together to find the formula for the nth term. The first term is 3. Then we have the common ratio, 1/3 to the n minus 1 power. So that is the answer. Now we're going to start looking at sums of geometric sequences. So here is the partial sum adding up the first n terms. So we have a formula for that right here. So notice what you need. You need the first term, you need the common ratio, and you need how many terms you're adding up. So let's try that formula with the next example. Find the sum of 2 plus 6/5 and so on and so forth. One thing to note is this last term is always to the n minus 1, and we have that here as well. So it's not giving us a stopping point. So we're just going to write out the general formula, and then we'll go ahead and simplify it if possible. So the sum of the first n terms will be the first term, which is 2, times 1 minus, okay, r is given right here, 3/5. So 3/5 to the n power over 1 minus r 3/5. So we can't really get a number from this because we still have an n here. But what we can do is simplify it a little bit. So this will be 2 times 1 minus 3/5 to the n power over 2/5. 1 minus 3/5 is 2/5. So I can change that to multiplying by the reciprocal. So 2 times 5 over 2 times this numerator that's left, 1 minus 3/5 to the n. So the 2's here cancel, right? So I guess this might be the best we can do as a simplified version. It's 5 times 1 minus 3/5 to the n power. So by simplifying it, if you went back and someone said, okay, the first 10 terms, you could plug in 10 for n, right? But this just asks for, in general, the first n terms. Okay, we have something special in this section called an infinite geometric series. You'll notice something a little bit different about this summation, and hopefully what you're noticing is this infinity. So what you're doing is you're adding up you're adding up all the terms, every single one, and so the sum will be infinite. So what's interesting is sometimes you can actually find that sum. The sum isn't always infinity. Sometimes it actually is a number. When it is a number, we say that it converges, and the only time it converges is if this is the case. If the absolute value of the common ratio is less than 1, then the infinite geometric series will converge. Not only will it converge, you can actually find what it converges to, and that will be the first term divided by 1 minus r. It's a little counterintuitive at first to think that you're adding up infinitely many numbers and you're actually not getting infinity. But if the common ratio is less than 1, then the terms are getting smaller and smaller and smaller. So this is something you'll investigate more in Calculus 2. So let's try an example. Determine whether this series converges or diverges. If it converges, find its sum. So the way to determine if it converges is to find the common ratio and see if its absolute value is less than 1. So to find the common ratio, I can divide consecutive terms. So I'll take the second term and divide it by the first term. So 9/16 times -4/3. So I'm seeing some reducing. 9 over 3 is 3. Taking out factors of 4. So when I divided the terms, I got -3/4. So I would get that no matter what terms I divided, as long as they're consecutive. So the common ratio is -3/4. So obviously the absolute value of -3/4 is 3/4, which is less than 1. So what that tells me is the geometric series converges. And because of that, we can now find the sum using the formula from above. So for the formula, which I'll write right here. We need the first term and we need the common ratio. Well, the first term is negative 3/4, and the common ratio is negative 3/4. They won't usually be the same, they just happen to be in this example. Okay, so we'll plug these in. So the first term is negative 3/4 divided by 1 minus the common ratio. So that's negative 3/4 over 1 plus 3/4. So that's 4/4 plus 3/4, so 7/4. And then we can multiply by the reciprocal. Negative 3/4 times 4/7. The 4's cancel, so negative 3/7. So the sum converges to negative 3/7. And we do have one last example in this section. A ball is dropped from a height of 30 feet. Each time it strikes the ground, it bounces up to 0.8 of the previous height. What height will the ball bounce up to after it strikes the ground for the third time? Okay, let's try that. So you drop the ball from a height of 30 feet, so it travels 30 feet to the ground, then it bounces upward. So let's find the height of the first bounce. So that will be the previous height, right, which is the original height, which is 30, times 0.8, right? So the first bounce, it will bounce up to 24 feet. The second bounce, you take the previous height of the ball, which was now 24, multiply that by 0.8. So after the second bounce, it will rebound up to 19.2 feet. So the third bounce, that's what we're being asked to find, we take that previous height and multiply that by 0.8. So that would be 15.36, feet. Feet. Okay, how high will it bounce after it strikes the ground for the nth time? So you probably have noticed a kind of a pattern here. The common ratio being 0.8, the initial first term being 24, right? Because I'm treating this as a sub 1, a sub 2, and a sub 3. So the first term is 24 times the common ratio to the n minus 1 power. Okay. Part C. How many times does the ball need to strike the ground before its bounce is less than 6 inches? First of all, be careful. The problem has been in feet all along until this one. So 6 inches is 0.5 feet. So I'm going to convert that to feet, and then we'll just set up an equation. How many times or how many bounces do we need to get to that that kind of a small rebound? So I will set this equal to the formula for the nth term. That way we can solve for n. So let's first of all divide both sides by 24. I'm just going to leave this as a fraction and put the whole thing in the calculator later. Okay, my unknown is in the exponent, so I do need to use a log or a natural log. I think I'll use a natural log on both sides so that I can get that down from the exponent position. Okay, so I have the natural log of 0.5 over 24 equals n minus 1. So this was the whole point of using the log, to use this property of bringing that exponent down to the front. Let's divide both sides with a natural log of 0.8. So I have the natural log of 0.5 over 24 divided by the natural log of 0.8 equals n minus 1. So the exact answer would be natural log of 0.5 over 24 divided by natural log of 0.8 plus 1, which I put into my calculator earlier. That's about 18.35. So it's going to take until the 19th bounce for the rebound height to be less than 6 inches. 18.35 isn't doesn't make sense, and it's supposed to be a whole number, so we'll go to the next bounce, right? Because the 18th bounce is probably still getting higher than 6 inches, but by the 19th bounce, it should be getting shorter than 6 inches as it bounces back from the ground. So for this particular question, the common ratio was 0.8, which is less than 1. So if we added up all the terms or all the bounce heights, we should get a number. It should converge. So that's what part D is about. What total vertical distance does the ball travel before it stops bouncing? So first of all, we know that when you drop it, it falls 30 feet. Plus, now all the bounce heights after that. So that would be the first term, a sub 1, divided by 1 minus the common ratio. So that would be 30 plus 24 divided by 0.2. So that is 30 plus 120. So 150 feet is the total it travels. So just to point this out, this is the initial drop of the ball. So that isn't a bounce, right? That's where it's being dropped from. But that does count as far as the total vertical distance. So I'm just making sure we add that in. And this is all the bounces. Okay.